Hello everyone, in this video I'm going to be talking through how to measure viscosity and what we actually mean by that term. Now the easiest way to think of this particular scientific term is if we imagine that we've got a person there and they've been asked to run through some water. So if you ask them to run through some water, they'll find that fairly easy, really straightforward to do. Now if you ask the same person to run through, let's say, some treacle, that would be far harder. The amount of force required to move through the treacle would be far greater than that required to move through the water. So we actually say that the treacle is more viscous. So viscosity of a liquid, and at the top we'll just put its symbol, looks like an unusual shape N, so we're going to use that symbol for viscosity. Viscosity of a liquid is a measure of its resistance to flow. So we'll just put that in there. It's a measure of the resistance to flow. That the key thing there, resistance. So the more viscous a fluid is, the harder it is to flow through it. And it depends largely on two things: the structure of the molecules within the liquid and their arrangement. So the structure of the molecules and their arrangement will dictate how viscous that particular liquid is. Now you can measure this, you can calculate values for viscosity very easily within a lab. So we've got a piece of equipment here. It looks like a typical measuring cylinder used in the lab, but this one has a particular special name. This one is called the Jeffreys tube. So we'll just label that here. This is our Jeffreys tube. And into our Jeffreys tube we have a fluid, and we'll say it's treacle again. We'll just use that as an example of viscous liquid. So fill that up there, and we'll label that one. So we've got some treacle, but this could be any viscous liquid that we're testing here. Now what there are markings on the side of this Jeffreys tube, and we're going to use this to get a value for distance and the time taken for a particular object to move a set distance to obtain a speed. Now, what we have at the top of this Jeffreys tube, I'm just drawing in red, is a ball bearing. So we'll just label that one there. We've got this special ball bearing. Now before this practical, what we need to do is work out the diameter and the mass of the ball. We'll come back to that in a moment, but having found the diameter and mass of the ball bearing, what we're going to do is we're going to drop that into this Jeffreys tube. Now it will actually reach terminal velocity fairly quickly. So it will reach that maximum falling rate quite high at the top of this tube. So we want to really start timing about 2 ball bearing diameters worth from the top of the tube. Maybe just where I put this particular line across here, and finish maybe at the same point. So 2 ball bearing diameters worth at the bottom. And what we're going to do is we're going to start the timer when we cross line 1 and stop it when we cross line 2. We know the distance because we're going to use our markings on the Jeffreys tube. We look at the time it takes to move from line 1 to 2, and from that we can work out a speed. But more than that, what we can do is work out a value for viscosity. Now viscosity, the formula for viscosity rather, uses something called Stoke's law. So we'll just mention that now. So we're going to come on to what's called Stoke's law. An apostrophe there. Now Stoke's law says that F, where F is the force due to the viscous drag of the liquid, is equal to 6 multiplied by pi, which we use, take a value of 3.14 for that, multiplied by this value for viscosity, so we've got this symbol for viscosity here, multiplied by the radius of the ball, multiplied by v, the speed of the ball bearing, and that's calculated by the distance fallen, measured in meters, divided by the time taken, measured in seconds. Now, when the ball bearing is moving at a constant speed, the upward force due to the viscous drag of the liquid will equal the downward force due to gravity. So we can say that the force due to gravity is equal to the mass of the ball bearing. So if we take the value for G for gravity is 9.81 meters per second squared and times that by the mass, that will give us our value for F, our force. So in another video I've talked about how you can calculate force from mass times gravity. If we take gravity, the value for G is 9.81, then doing mg will give us the value for F. So you can actually rearrange Stoke's law. Now we've got a value for F to just get this particular value here, a value for viscosity. And if we rearrange this formula, it essentially becomes viscosity equals mg, and that represents our value for force, over 6 pi, that's the value for pi, rv. R being the radius of the ball bearing and v again being the speed that we've calculated it moving. So it's possible using set values to actually calculate a value for viscosity. We just do the mass times gravity, or in this case 9.81 meters per second squared, divide that by 6 pi rv. Now this experiment can provide really important information, especially about the flow of liquids and gases in things like pipe work, because dust, dirt, temperature differences, water content, gas bubbles, all of those can actually affect the viscosity of a liquid and gas. So it's important to be aware of those, and so that you can investigate them, and so you can obtain the maximum amount of flow that you need. So that's just a little bit about viscosity. It's a measure of a liquid's resistance to flow. We can demonstrate it in a lab using the Jeffreys tube. We drop a ball bearing in, we measure over a set distance the time it takes to drop. We get a value for V, the speed there, and using the mass of the ball bearing and the radius, we're able to calculate, using Stoke's law, a value for the viscosity of that particular liquid. Okay, hope all that helps.